It was actually her idea that I come. Yeah, I don't know what the hell she's doing with me. She could do better. All right. All right. Off of 232, let's move to or 332. Let's move to 342. Yeah. All right. Tonight, I'm sorry I'm behind on grading homework. I'm getting to it. It's just I'm getting to it. Tonight we're going to talk about searching data. And it's kind of interesting that we talk about searching data before we talk about sorting data, which is interesting. But it's grouped together with hashing. So we're gonna talk about hashing of data, and you're going to get a homework assignment that has to do with hashing. Man, when we got in here, the door was open and it was 82 degrees in here. Wow. So, all right. Next week, we're going to talk about sorting of data. So this week, we're just going to talk about searching. When it comes to searching it, there are really only two kinds of ways to search data. There's a linear or a serial search, which is just a for loop. Start at the beginning, go through it until you find what you're looking for. And the other one is a binary search, which ends up being a big O of log n. So with a big O of log n, you're not going to get any better than that unless you have a priori information that tells you where this lives inside the array. And interestingly enough, that's what hashing is. So what we're going to talk about first is how do we search for data. With a linear search, I mean, it is literally a for loop. And that's, you know, that's a linear search. Now this is a pretty crappy linear search, and there's a reason for it, is that when you get to the end, how do you know whether or not you found it? So if we start executing this line of code here, how do we know under what circumstances we left that loop? Because there are two things that could have happened, right? Is we could have gone all the way through the array and not found what we were looking for, or we found it and we jumped out. How do we know if we hit this statement which path we took?
We have to set up a Boolean variable?
We could set a Boolean variable that says it was found. We could do that, or we can also just do this, right? What if we do that? What happens? We have a value that can live outside of that for loop, right? So if we get down here and I is equal to array.length, then what does that mean? We didn't find it. If it's any other value, that means we found it at that location in there. So yeah, a Boolean is absolutely something you can do, but it's not going to give you an index into which one it was that you found it with. So typically what you'll want to do is something like this, where you move the declaration of this outside of this scope so it can live outside of here. And that's it. That is everything there is to know about linear search. Linear or serial. One after another. It's a linear process. So, considering we call this linear search, what do you think its big O looks like? N, right? And on average, it's going to take you probably, you know, array size plus 1 over 2 to find what you're looking for. So basically, you got to look, on average, you got to look through half the data to find what you're looking for. Sometimes it's the first thing, sometimes it's the last thing. Yeah, but this has a big O of N. Now, is linear good enough? For most things, yes. Because there's a couple advantages to having something where you can linearly search for it. First of all, you don't have to sort it. You don't care what order it's in, because you're going to take a look at everything in there anyways. And by doing that, that will benefit you if there's a ton of data and you would need to resort it each time you add something new to the data. But you also get to the point where the data becomes too large, where a linear search takes too long. And with the advent of more and more powerful processors, the length of a linear array that you don't want to be linearly searching anymore, it's pretty big these days. I mean, 100,000 is nothing. So you have 100,000 items in an array, and a lot of it depends how frequently you're going to search the data. If you're only going to search it occasionally, it doesn't make sense to sort it. If you're going to search it repeatedly, it makes sense to sort it, because then you can use the binary search, and the binary search is big O of log n, which is a far, it's a much better way to play as far as your data is concerned. But, and I can't stress enough, the downside to a binary search is that the data has to be sorted. So each time you do this, you have to sort it. Next week, we're going to talk about sorting. We're going to talk about linear, or we're going to talk about quadratic sorts, which, gee, what do you think the big O on those guys is? And squared, I bet. And then we're going to talk about some recursive sorts, which will get down to like a big O of n log n, which is slightly worse than linear, because it's a logarithmic times a linear, that kind of thing. But once the data is sorted, I kind of prepped you for this in the first class of this semester. It's like, I'm thinking of a number between 1 and 1,000. What's your first choice? 500. Divide it in half. And if I tell you that, hey, that's too low, your next choice is 750, right? What you're doing is you're dividing it down each time. Divide it in half, divide it in half, divide it in half. Well, we can do the same exact thing with an array. So you have, I mean, if you think about it, if I'm thinking of a number between 1 and 1,000, it's basically just an array with all the numbers between 1 and 1,000. Go to the 500th index. It just so happens that the index is equal to the number, but it's exactly the same concept. So now what we can do is we can say, oh, okay, so let's take a look at what's going on inside of there. So we start out and we say, all right, so I need a low is equal to 0. I need a high, which is equal to array dot length minus 1. And that's basically everything that we have, right? 0 through array. That's our whole thing. Now, what we want to do is we're basically going to do a while loop, and there's going to be some as yet to be named Boolean expression that will live inside here. And then what we're going to do is we're going to say int mid is equal to low plus high divided by 2. So when we first start out, it's going to basically pick the middle of that. Now, what we're going to do is we're going to say if array sub mid is equal to the data we're looking for, and then this basically means we're done, right? So this means we found it. And right now, all right. Now, let me give you a little prep work here. If we were doing this recursively, that looks a lot like a base case, doesn't it? It is. We'll get there. So now we know if the the low plus high divided by 2 is equal to mid. Array submit is equal to the data we found it. And that's the same thing, like I'm thinking of a number between 1 and 1,000. First guess, 500. Now I have to remember this does integer math, so things are truncated. And that's why when we were talking about this guy here, as to how much it does, that's why we did a n plus 1 divided by 2. So that way it takes care of that integer math problem. So here, now we didn't find it. What do we have to do next?
Lower or higher?
It's lower or higher. So if that's greater than data, then what does that mean? That means that our data actually lives in the first half of the array, or the half of the part that we're looking at, right? So what would we do in order, because we're going to recalculate that mid each time we loop back around. So our two variables that we can play with that move us through this are low and high. We'll use those to recalculate the mid. So if the array mid is greater than the data that we're looking for, that means it needs to live earlier in the array. So what we'll do is we'll just say that high is equal to mid minus 1. So now, next time we come back up, we'll actually be looking at the spot when we first started out. We'll be looking at between 0 and mid minus 1 would be the area that we'll be looking at next. And then we'll take the middle of that and do that. So that's all that that guy really needs at that point in time. Else, what happens is low is equal to mid plus 1. Because if we want to look in the second half of it, we'll say our low is starting at the second half of this. Now, you know, when you look at the low plus high divided by 2, it works, okay? It's not going to have a problem because, I mean, if we started out with, you know, well, we had low was 1 and high was, all right, let's do this. Low is 0 and high is 99. And then we divide that in half. 99 divided in half is actually going to be 48, or 49. So mid is 49. And then what happens if we decide it comes further down through that, then what we would do is we say low is equal to 50. So now we have 50 plus 99, which gives us 149. Divide that in half, and that gives us 74, right? So if this is between 50 and 99, then this becomes 74. So you can add the low and the high, and you can just move those, and the math still works because it puts you in the right spot of the array. So that's why we don't have to go, oh, well, shouldn't we calculate the difference between the... No, you don't need to worry about it. You can just add the low and the high and divide it by 2. So now we have this and this. So this has given us most of the solution, right? We can find it, or we can change the data section that we're looking at in the array. The only thing we haven't done is figured out how to know if we haven't found it. So, believe it or not, that's what's in the while up there. That's what's going to tell us that we've spent too much time looking, we've looked at everything that we should, and we haven't found it. So how is that going to happen? Let's take a look at a small array and see what happens. Here's our sorted array. TED, not TID. That's computer joke. crowd, tough crowd, tough crowd, tough crowd. Where's my daughter go? That's such a dad joke. All right, so let's say that we're searching for, just if you ever have to teach this stuff, find the middle and pick the number just one before it or one after it. Those are the most difficult numbers to find. 1, 2, 3. So this is 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 divided in half would give us 4. So we'll look for this guy. So we're searching for 11. So data is equal to 11. Low is equal to 0. High is equal to 9. And mid is equal to 4. And away we go. Right? It's basically everything we did there. Right? So low is equal to 0. High is equal to array length minus 1. And inside here we said mid is equal to low plus high divided by 2. Everybody with me? All right. So what do? We say if array sub mid, which would be this guy, is 11, which it isn't. Now what we want to figure out is where do we need to go from there? If array sub mid, which is 15, is greater than data, which it is, we're then going to change high to be equal to mid minus 1. So this becomes 3 at that point in time. Because here's mid minus 1. Then we repeat the while loop. And what happens now is we say, okay, mid is now equal to 0 plus 3 divided by 2, which means this is now 2. All right, and then we go, is array sub mid equal to what we're looking for? No, but it's higher this time, right? So what will happen is this time we'll actually set this to be equal to that. Now it's pretty obvious if they're both 3, 3 plus 3 divided by 2 is going to give us what? 3, which is the one that we're looking for. So then this becomes 3, and away we go. Pretty straightforward, isn't it? It works. It's really efficient. Now, let's say we're looking for the number 12. So instead of 11, we're looking for 12, which doesn't exist. This is 0, this is 9, this is 4. So we come through and we say, okay, is it at 4? No, it's higher. So what we want to do is we want to convert high to be mid minus 1, and it should live in this section. We come through here, we recalculate mid, where this is 2. Is array sub 2 what we're looking for? No, but it's higher. So this time we'll go through and we'll change this to be 3. Now we come down here and mid is now equal to 3. And we say, is this equal to the one that we're looking for? No. But the one that we're looking for, array sub mid, is less than the number that we're looking for. So at this point in time, what would we do?
You would make low mid plus 1.
Yep. So low becomes mid plus 1. This becomes a 4. And at this point in time, we're pretty much done, right? So what's going on here that indicates that we couldn't find what we were looking for?
Low is higher.
Yep. Low is higher than high. So this becomes while low is less than or equal to high. Or you can say while high is greater than low. But it has to be less than or equal to, because when we found the number, low and high were exactly the same, and then the next time we calculated mid and we found it. So it can only be when low is less than or equal to high. Now, what's going to happen is when we found it, we may just, you know, we may put a statement in here that looks like this, right? Return mid. Gives us the index into the array where the value we're looking for fits. And down here, because we would have fallen out of here, we could just return -1. And then install this whole thing inside of a method. That's a binary search. Does this make sense? Now for the fun part. Let's implement it first, and then we'll come back and we'll say, hey, now that we have this implemented, what if we wanted to do this recursively?
What's the big old behind this? N? N? Huh? See, it says linear. Big O is.
Today is 16th of April.
Oh, I see what you mean. Okay. Was it quad? Upper binary search?
Make sure you get your taxes in by the end of the day tomorrow. Say that again? Make sure you get your taxes in by the end of the day tomorrow. It is, but April 15th is Patriots Day in Massachusetts, so all the government offices are closed in Suffolk County, and so they don't take the taxes on. The 15th is a holiday in Maine and in Massachusetts. And then 16th of April is Emancipation Day in Washington, D.C., so the government's closed then. So if you don't have it in by the 15th, you have to have it in by the 17th. I know, because I usually owe money, so I wait until the very last minute for my taxes. All right. Here's our binary search. We're going to do everything that we did there. We're going to say int low equals 0, int high equals array dot length -1, while low is less than or equal to high. If array sub mid is equal to data, return mid. If array sub mid, make sure I got something I did here. Array sub mid is greater than data. Array sub mid funny, red lines go away and it looks like it's kind of happy. So now we can test it. And in order to test it, we need an array. So int array equals, and it has to be sorted, right? Alright, so now we have our sorted array. And then what we can do is we can say print out, we want to print out in search array, comma, 20. Now, if we run this, terminated. Doesn't help. It helps. We kind of have to like call it in order for it to work. All right. 8. 0, 1, 2, 3, 4, 5, 6, 7, 8. Woohoo! Alright, let's try it with let's try looking for 21. That's it. And binary search is one of those questions you're going to get on a job interview. So somebody's going to say, "Hey, write for me a binary search." This poor guy over there, his hand's going to get tired. Is it better? Alright, so that's it for a binary search. Well, that's the iterative solution of a binary search because it all takes place inside of a loop. A while loop in this case. But that's it. No magic, nothing else. That's the whole shooting match. And that's as good a search as you get. So this is a really good one to keep in your bag of tricks. So you make sure that you're able to implement this. Now, let's take a look at this and break it down a little bit as to what we could do to make this be recursive. We have a couple base cases, right? We have a base case where array submit is equal to the data and we're done. We also have a base case where low is greater than or greater than high. So if low is greater than high, then we can basically stop for those two reasons. One we stopped because we found it, one we stopped because we didn't. And funny, a binary search, it only has two outcomes, right? Yes, no. Found it, didn't. So if we want to take this and put this into a recursive binary search, it looks kind of like this. Now, a couple things that you have to remember is your context has to travel with you, where it doesn't have to travel with you in the iterative version because it all takes place inside of that one method. But now we're going to be calling ourselves again. And in the process of doing that, we need information. We need low and high to travel with us. We can recalculate mid each time through, but each time we come through, if we don't know what section of the data we're looking at, we're kind of lost at that point in time. So what's going to happen is that this is going to carry with us the array, the data, low, and high. These are the pieces of information we need to do this. Now we're going to call this thing differently, of course, because the other one we just called passing the array and the data we were looking for. This one, a call to this is going to look like rec bin search array data 0 array length -1 would be what we do this. So a lot of times you might write this as a private and then have a public wrapper that would turn around and call this guy for you. All right, so what happens in here? We need to know int mid is equal to, well, yeah, look at there, mid equals low plus high divided by 2. Should look familiar. Oh yeah. No, I like it better like that. All right. So now we have mid. But one of the things that may have happened before we even got there is one of the other ones, right? If low is greater than high, return -1. Because we're kind of done at that point in time. Otherwise, calculate mid, and then what happens here is we ask the question if mids or array sub mid is equal to data, then we return mid. Now for the other section, if array sub mid is greater than data, then instead of recalculating the low and the high, we're just going to do this. We're going to return rec bin search array data. Now, instead of recalculating high, we'll leave low alone, but then we'll say mid -1 is what we'll pass as the last argument. Else, return rec bin search array data mid +1 high. All right. So, oops, if you call array. That's the way we can do this. Put it back here. Make it look all Java-y. What do you think? Does it look like it'll do it? I think so. But one base case, second base case, and then all the recurring. That's basically it. And like this one here, if you look up there where it says if array sub mid is greater than data, then high equals mid -1. So we pass mid -1 in here. And the opposite of it is we say that low equals mid +1, we pass in mid +1 there. Let's see if it works. Search. It needs more parameters. 0 array dot length -1 0 array dot length -1. All right. We run this. What do we get? Same results. Yeah, that's right. When I have first-time job seekers and I'm interviewing them, I like this one because it tells me you understand searching and you understand recursion. But I have been known to ask both. Okay, show me both of them. Show me an iterative binary search and a recursive binary search. These ones you should know. I mean, there's no reason why you shouldn't just be able to whip one of these out. Boom, done. Make sure it makes sense. Make sure you become comfortable with it, that you understand what it is that it's doing. That's a big deal. Questions? Observations?
When would you use recursive versus iterative in like a real world use case? Like how would you choose?
It really doesn't matter. I mean, and typically what you're going to find out is that an iterative solution is pretty uniformly more efficient than a recursive solution. But if you think about something, if you have 4 billion entries in an array, the worst case you're going to get is a recursion depth of 32. So the odds of you blowing out the stack are pretty low as far as this one's concerned. But the iterative one is going to be more efficient because it's not making method calls. The recursive one is making method calls. Why would you use one or the other? I don't have an answer to that, sorry. Depends on the size of your stack.
Is there a standard one?
Standard JVM stack size, I think, is 5. Actually, it's pretty small. It's like 16K or something like that. Actually, relatively small. You can change it. Two megabytes, according to this. Let's see. I want Java. So it helps if I put Java instead of Java.
Jara.
Java. Windows default thread stack size. No. How big is the stack in Java? Java virtual machine has a default size for threads. Call stack from 1 megabyte. Raise the stack limit for, so it looks like 1 megabyte. And you can grow it. And let's take a look at something. It's right there. You can use the option -XSS 1M to set it to 1 megabyte. So we're gonna need that in a minute because here's what we're gonna do. What we're gonna do is we're going to add to this an iterative search. Public int it search. Array int data. And inside here for int, here is int I. For I equals 0, I is less than array dot length. Plus if array sub I equals to data, return I. Return. Okay, so there's our iterative search. That's all there is to it. Pretty straightforward. And just to make sure, we can test it up here to see if it works.
Question.
Yep.
This, maybe wrong with the building, but that thing, I outside.
Right, you don't because,
You're not gonna use anything.
right. If we were using it further down inside here, then we would do that. But in the case of this one, we don't really need to do that. All right, if we run this for all these guys, we get all the right answers. All right. Now, let's play around with them. What we want to do, though, is we want to figure out when does a binary search become more efficient than an iterative search. And the best way to do that is to search for something that isn't in the list. And like I said, if you wanted to have the most search for a binary search is one element short of mid, because it goes in half, 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 till it gets all the way down to that single element. So what we want to do is we want this section of code we really don't need anymore, so we'll just comment that out for right now. And then we'll come down here and we're going to build an array. Int array2. Right. Now, we need to know something. So what we're going to do is we're going to say int array. Yeah, let's do it that way. So we'll go int, let's go final int array size equals, let's go with 1,000. All right, so now we have our array size is equal to 1,000. Then what we'll do is we'll say array2 equals new int sub array size, and now we need to fill it. We don't really care how we fill it, so for int I equals 0, I is less than array2 dot length I plus. All right. It has to be sorted. So I mean, we could just go 1 through whatever, or we could do it times 5s or whatever. Who cares? So we'll just do it. Array2 sub I is equal to I times 2. And that will build us a sorted array. Okay? And we're all done. Now with 1,000 in it, what we know is that it's going to go from 0 up to what?
999.
Times 2. Right? So it should give us basically 2,000 minus 2. So 1998 should be the biggest one in there. But what's kind of neat is we can go, okay, let's search for there. Wrong button. What I want to do here is we'll say if search array2 comma array size divided by 2 minus 1. So in the case of 1,000, that should give us 499. So if we run this now, we should get an index that looks like minus 1. Yeah, because that one's not there. If we do this, 250. Array size divided by 2 comes in at index 250. Because in order for this thing to really work, we kind of have to do this, right? Because we're going up by 2s. So if we run this now, we get 500. If we subtract 1 from this, this won't find it, but in the case of this one, it has to go all the way through to the end of the array. Now if we take this same one, and instead of doing the iterative search, we do the binary search. It too should not find what we're looking for, which it doesn't. One of the things we don't know is how many searches did it take in order for that to work. So what we can do inside here is we can say int count equals 0. Each time we pass there and we haven't found it, we say count plus plus, and then at the end here, if we do find it, take that same statement there, and we'll pop it down here. All right, so now if we run this, we get 9 searches on 1,000, which is correct. So if we do this with 10,000, and we run this, we should get like 13 for the binary search. The linear search is going to take us all the way down to the end. Now, for the next piece of information. First of all, we're going to change the order of these. So it looks like this. Because the binary search, even if we had 4 billion things in there, it's only going to take 32 searches to find that it didn't find it. All right. So we want to figure out how long is this going to take. Well, in the system object, there's this wonderful thing called current time in millis, and it's a long. So what we'll say is long start 1 is equal to system.currentTime millis. And then what we'll do is we'll try to search for this in the binary search, and then what we will do is we'll say that the binary search took double quote marks. Binary search took plus start 1 minus system dot get current time millis. Actually, it's the other way around. That one minus start 1. That'll tell us how long it took to do that in milliseconds. And then we're going to do the same exact thing down here. Long start 2. Actually, just steal that code from here. All right, so there's our start 2, and then what is this having a problem? Operator minus is on the A. Okay. Alright. So now we're going to steal this section of code here, and we're going to put it down here. And iterative search took that one start 2. Alright, so now we're at 10,000. Run this, we see this. Count equals 13, binary search took 0, iterative search took 0. It means completed in less than a millisecond. So now if we say, okay, let's go to 100,000. The binary search took 16, the iterative took 0. One thing you have to remember here is we're not the only thing running on this system. So other stuff could have swapped this out, all that kind of stuff. So if we run it again, still not that big a deal. Bump it by another 0. The iterative is looking a lot more like a real number. All right, another one. Yeah, we don't get any zeros out of the iterative anymore. Now, what do we got here? What is that? 3, yeah, that's 10 million. There's 100 million. Took a little longer now, doesn't it? 63, 47. Now, I don't think we can go to a... We might be able to get away with a billion. Nope. Out of memory error. So now we need to actually change this guy so that it will do what we want it to do.
That's the array size, right?
Yeah, the array size blew out the memory. Now, wait a minute, it's not here. It's going to run. Run configurations. All right, so arguments, JRE, here we go. Here's our execution environment, here's our environment. Environment variables set, main, program arguments, VM arguments. Dash XSS equals 5 megabytes. Yeah, probably got that wrong. Dash XXS 1 dash XXS 1 megabyte. Okay. That looks right. Let's try one. That creates a job for virtual machine. Alright. Not quite right. Oh, okay. According to that, we want this to just be that. Okay, that ran. So now we can change the configuration so that it's, instead of 1, let's set it to 5. Still out of memory. Okay, 50 megabytes. Still out of memory. $500 megabytes. Still out of memory. Still out of memory. How's that happening? Anybody want to take a stab at it? What are we changing? The stack size. We're not changing the heap size. And we need to change the heap size.
Yeah, it's not recursive.
Huh?
It's not recursive.
Yeah. Dash X MS. You can set the minimum heap size with dash MS and so minimum and maximum. Minimum dash MX. Okay, let's try that. we need that much. Let's try that. Let's go, How do I keep space? Right one? I don't know. Why don't you take 5? I'll find it. When you come back.